All right, let's have a look at escape speed. The guiding question here is, how fast must a rocket launch to escape Earth's gravitational pull? So let's first talk about escape energy. Every mass has an energy that gravitationally binds other objects to it. This binding energy is the amount of additional kinetic energy needed to escape the gravitational force of the mass. In the case of a rocket on a planet, this binding gravitational energy is equal to the amount of kinetic energy needed on the surface of the object to reach an infinite distance away with zero kinetic energy left over. The escape speed is how fast the rocket must be traveling to escape the planet's gravitational force. Now, this doesn't have to just be for a planet. It could be for a star. It could be for a black hole. But we wouldn't be using the surface in those cases because you'd be dead. All right, and looking at the derivation here, we're going to pull out this gravitational energy. And it's going to look a little strange because it has a negative value. Basically, the shape of the graph for gravitational potential energy is related by R, and this would be Eg, and it's an inverse relationship, and it's actually negative. So the graph kind of looks like this in the fourth quadrant, but I'm not going to have you guys look at that. I'll just show you the derivation for it. So the change in kinetic energy is equal to negative the change in the gravitational potential energy. So we're going to consider an infinite distance away being the final point. So here we'll have kinetic energy final subtract kinetic energy initial is equal to negative gravitational potential energy final subtract gravitational potential energy initial. Now we can do a little switcheroo here, which kind of makes things nice. Another thing we can do is consider that when you're an infinite distance away, you're going to have a zero speed, so this whole term goes to zero. Another thing that we'll look at here, we'll have EKI negative is equal to EGI minus EGF. Just distributing that negative, but you'll see it will come back in just a moment. So EKI negative 1/2, the mass of the rocket, its speed squared, is going to be equal to EGI is negative G, the mass of the planet, the mass of the rocket, over the radius of the planet, minus a negative G mass of the planet, mass of the rocket, over this infinite distance away. Now I'm going to do something that's not really beautiful, but when we look at anything divided by infinity, this whole term goes to zero. So what we end up with, we've got these negatives in front, and we're just going to get rid of those now too. Multiply everything by -1. We end up with 1/2 the mass of the rocket, its speed squared is equal to G, mass of the planet, mass of the rocket, divided by the radius of the planet. You'll see here that the mass of the rocket, or whatever object it is gone. It cancels out. And if we rearrange this, V squared is equal to 2G, the mass of the planet, over the radius of the planet. And then in our next step, we'll just take the square root. 2G, mass of the planet, or whatever object is being escaped from. So this here is the escape speed. I want you to try using it in this situation here, basically figuring out how fast you would have to leave Earth in order to go so far away that you wouldn't feel Earth's gravitational pull anymore. And again, this is not how fast you have to leave Earth in order to get to space. That value would be less than the escape speed. And then another question to consider, if that mass of the rocket canceled out, why are rockets so heavy? And how does that factor in here? So have fun with those.